Now we will go through another problem from the Thevenin's theorem and Thevenin's and Norton's theorem. So now this problem is according to the given problem, it's the AC circuit. So theorems in AC circuits. Now we have to discuss the topic. So now the complete circuit is connected with the R, L, C parameters, resistor, inductor and capacitor and excited by the AC source. The AC source is voltage source value is here 100 with angle 0 degrees with voltage source is there. Then convert the complete circuit into Thevenin's equivalent circuit. Convert the complete circuit into Thevenin's equivalent circuit. So the Thevenin's equivalent circuit explains the one voltage source. Now it's AC source, so we have to draw AC source here. Thevenin's equivalent voltage and impedance. Impedance is now it acts as a Z Thevenin's. So the complete circuit is replaces with the Thevenin's equivalent circuit. The Thevenin's equivalent circuit consists one voltage source and one impedance, both are in series. Now here I wrote impedance because the circuit is AC circuit. So if the circuit is AC circuit, here you have to write impedance. That impedance is also called as Z Thevenin's or ZS, source impedance, or equivalent impedance is Z Thevenin's, and this voltage is V Thevenin's voltage. So V Thevenin's voltage is nothing but open circuit voltage and Z Thevenin's is nothing but equivalent impedance between A and B terminals. Now we have to find out those analysis here. So to find that analysis purpose, according to the given circuit, here I am taking 100 volt voltage source. So in parallel cases, voltage source is voltage value is same value. So here voltage across inductor is 100 volts and voltage across capacitor is also 100 volts. So indirectly this voltage is here 100 volts. Indirectly voltage at this point because these two elements are connected in parallel combination. If the parallel combination, potential difference between the parallel combination is always same voltage is there. So 100 volts is applies across the J2 and across the minus J6. So at this point voltage is 100 volts. This 100 volts is divided into two elements here. One element is 3 ohms resistor, another element is J4 resistor is there. J4 inductance here, that value is, so now I am taking as a impedance. Impedance is J4 ohms. Two impedances are connected in series and it is excited with the 100 volt source. Then we want voltage across these 2 points. This voltage is also called as Thevenin's voltage here. Thevenin's voltage or open circuit voltage. So according to the given problem, Thevenin's voltage is voltage across J4 and here voltage source is 100 voltage, 100 is there. This 100 voltage is connected to the two elements. Then we want voltage across one element. Then apply immediately voltage division theorem. So total voltage into same impedance by total impedance 3 plus J4. So write in terms of angles, 100 with angle 0 degrees is there into J4. J4 explains the magnitude is 4 with angle 90 degrees because J explains the 90 degrees by, and here 3 plus J4. So magnitude of this value is square root of 3 square plus 4 square. Square root of 3 square plus 4 square is directly gives the 5. Square root of 3 square plus 4 square is 5. So in division operation, multiplication operation, write always in terms of polar form representation. So write all these values in terms of polar form. Then the angle of this is tan inverse of imaginary term by real term, that gives it tan inverse of 4 by 3. Tan inverse of 4 by 3 is greater than the 1, so approximately I am writing here 53 degrees here. Because tan inverse of 1 is 45 degrees and tan inverse of 90 is infinity. So now in between is there, so tan inverse of 4 by 3 greater than the 1 value, then I am writing approximate value is 53 degrees. Then simplify this here. So after simplification here 5 and 100 is there. So 5 fours and this gives it directly 20 into 4, 80 with angle 90 minus 53. Phases are subtracted. 90 minus 53 is approximately equal to 37 degrees. This is V Thevenin's voltage. So finally we got open circuit voltage, V Thevenin's voltage. And immediately we have to find out Thevenin's impedance. So to find the Thevenin's impedance, just find the impedance between these low terminals here, open circuit and low terminals. And to find the Thevenin's impedance, again we have to apply the same technique. The technique is if the circuit consists only independent sources, remove all the sources. Now here the circuit consists only one independent source is there, then remove the source here. This source is acts as a short circuit because it is a voltage source. Voltage source is acts as short circuit, and remaining elements here, inductor is there, and here one more capacitor, here resistor and inductor. This is the complete circuit now. So now we have to find out the impedance between these two terminals, that is Z Thevenins here. Z Thevenins. So this value is J4 and this value is 3, and here minus J6 and here J2. Now voltage source is short circuited. If these 2 points are short circuited, these resistors, these impedances are eliminated here. There is no use of these impedances because these impedances are eliminated. The complete current is flows through the short circuit path. So these two impedances are eliminated. Now one more impedance is their resistance 3 ohms and J4. These two are connected in parallel combination. So 3 into J4 by 3 plus J4. So 3 into J4 by 3 plus J4 because Z1 into Z2 by Z1 plus Z2 parallel combination. So this gives the approximately equivalent value is here 3 into J4, that is 12J, alright, with angles polar form 1290 degrees by this value just now we wrote here 5 with angle 53 degrees. 12 by 5, this value is approximately 2.4 because 5 to is 10 and 2.4 is there, 2.4 with angle 37 degrees. So Z Thevenin's value is 2.4 with angle 37 degrees and V Thevenin's value is here 80 with angle 37 degrees. So finally we converted the complete circuit. The complete circuit is into Thevenin's equivalent circuit. So this comes under AC circuits. In AC circuits, Thevenin's theorem. Network theorems in AC circuits. So AC circuits or DC circuit, we have to follow the standard procedure. If the circuit is AC circuit, just we have to find out impedance. If the circuit is DC circuit, there find resistance. That's it. So voltage and these parameters are same as it is here. So finally I converted the given circuit into Thevenin's equivalent circuit. This is one different method of problem here. And one more problem is given like this is another method. This is also one previous competitive exam question. And these methods of questions also very important. Here one linear network is connected here. One linear network. This linear network is connected with one resistor. Internally this linear network has a number of elements. Number of elements means sources and resistive element, all the elements are there. Finally the complete network is connected with one resistor, load resistor R, and the current through this current through the resistor R is there. Then some conditions are given here. Current through the resistor R is 3 amperes. Current through the resistor R is 3 amperes. So current through the resistance R is 3 amperes with resistance value 0 ohms. If this resistor value is 0 ohms, then the current through that resistance is 3 amps. And similarly, if the current through this is 1.5 amperes now, 1.5 amperes, if the resistance value changes with 2 ohms. If the resistance value is 0, this current is 3 amps. If the resistor value is 2 ohms, then this current is 1.5 amperes. Then we have to find out if the resistance value is 1, here we have to find out resistance value is 1, then what is the current through circuit, that what is I value. So to find this type of analysis, just to go through the network is linear network is there. This linear network is connected in between two terminals. Just assume these two are load terminals here, A and B. Any linear network is connected in between two terminals, then replace that linear network with a Thevenin's equivalent circuit or Norton's equivalent circuit, depends on the application. So take any one here. So just now I am taking here Thevenin's equivalent circuit. From the Thevenin's theorem explains any linear network is connected in between open circuit and load terminals. The complete network is replaced with equivalent voltage source. That voltage source is also called as Thevenin's equivalent circuit. Now I am replacing the complete network is with Thevenin's equivalent circuit with Thevenin's voltage, Thevenin's resistance. It's like this. So the complete circuit in between A and B terminals. In between A and B terminals, this complete linear network is replaced with Thevenin's equivalent circuit. And load resistor I am connecting as it is. This resistor is value is R. Then we want here current I. From this equation, from this circuit diagram, current I equation is now total voltage by total resistance. Total voltage by total resistance, that is V Thevenins by R Thevenins plus R, because these two are connected in series combination. Current is equal to total voltage by total resistance. I wrote this formula now. Now substitute the given condition in this. Current is 3 amperes, 3 is equal to, resistance is 0, substitute here R is equal to 0. So V Thevenins by R Thevenins plus 0, then directly which gives here V Thevenins is equal to 3 into R Thevenins. This is one condition. Finally we got Thevenins voltage. Thevenins voltage is 3 into R Thevenins, 3 times of the R Thevenins with this condition. Similarly applying second condition now. Second condition is current is 1.5 amperes. Current is 1.5 with the resistance value is 2. Substitute here resistance value is 2 in this. V Thevenins by R Thevenins plus 2. Substitute in that. Then multiply this side here. 1.5 R Thevenins plus 2 into 1.5 is 3 is equal to V Thevenins. V Thevenins is nothing but just now we got here 3 into R Thevenins. Substitute that value here. So here 1.5 R Thevenins and 3 R Thevenins. Take this is the side, then becomes 1.5 R Thevenins. R Thevenins is equal to 3 by 1.5. So R Thevenins is equal to, it gives you directly 2 ohms. Thevenins resistance is here 2 ohms. If the Thevenins resistance is 2 ohms, what about V Thevenins? V Thevenins is 3 into R Thevenins. So V Thevenins is 3 into R Thevenins. Now it becomes here 6 volts. Thevenins voltage is 6 volts. Finally we got this is 6 volts. And Thevenins resistance is 2 ohms. This is 2 ohms. Then we want current I with R is equal to 1 ohm. Then find here I is equal to V Thevenins is 6 by R Thevenins is 2 plus R is 1. So if we substitute all this value, then I it gives the 2 amps. So I value is 2 amps here. This is one different method question. Here network is not there. The network internal elements are not given. Just we have to assume the complete network is replaced with Thevenin's equivalent circuit, then substitute the given conditions. According to the given conditions, current through the one element is given with the different values of the resistor. Then I wrote like this here, then substitute in that, then you will get the answer. So these type of network, any linear network is connected in between load terminals, in between A and B terminals, immediately replace that network with Thevenin's equivalent circuit or Norton's equivalent circuit, depends on the question. So here we can use Norton's equivalent circuit also. So replace the complete circuit with Norton's equivalent circuit, one Norton's current and Norton's resistance both are in parallel combination, and connect this load resistor is parallel with that one. Then write there I equation is equal to current division theorem, Norton's current into R Norton's by Rn plus R. So that gives the current division theorem. So if you replace this complete network with a Norton's equivalent circuit, there apply current division theorem, then substitute these values, then it gives a direct answer. So here apply Thevenin's equivalent circuit, similarly try to practice with Norton's equivalent circuit also. So here I wrote the few solutions of the given problem. These are previous competitive exams questions, so don't neglect these problems, try to solve all these problems. See, from the network theorems, another important theorem is maximum power transfer theorem. So to understand the maximum power transfer theorem, again we required Thevenin's and Norton's. So already we discussed Thevenin's theorem and Norton's theorem. Now from that Thevenin's and Norton's, here we have to discuss another theorem is maximum power transfer theorem. So this theorem explains the power consumed, power dissipation of the load resistor RL is maximum with some conditions. So that means the network, the complete network is connected with one load resistor. The complete network is connected with one load resistor. So this load resistor consumes the power. That power the power consumption is maximum at particular condition. So that condition here we have to find out here. So for DC circuits and for AC circuit, different conditions are there. So first we will go through the DC circuit. So to understand this analysis purpose, initially I am taking one linear network is connected with a load resistor RL. So here I am assuming one linear network here. This is one linear network. This linear network internally, which consists number of elements, those elements are linear elements, and similarly some voltage sources also there. This complete network is connected to the load resistor RL here. Load resistor RL. So here I am taking this resistor is RL resistor. RL resistor. This resistor value should be variable resistor. This load resistor RL is variable resistor, means the load resistance is changes, resistance value is changes, power consumption of this RL is also changes. Then here we have to find out at particular resistance value, the power consumption is maximum, the power dissipation of RL is maximum. That value we have to find out. At which value this power consumption of RL is maximum, that is we have to find out here. So to find that analysis purpose, here always our required load resistor value should be variable resistor value. So it has to vary from 0 to up to infinity condition. At particular condition, the power consumption of the load resistor RL is maximum, then we have to find out that maximum power consumption. To find that purpose, this complete linear network now, this complete linear network is replaces with a Thevenin's equivalent circuit. Just I am replacing with Thevenin's equivalent circuit, or we can replace with Norton's equivalent circuit also, anyone here. So for easy simplification purpose, here I am replacing the complete network with Thevenin's equivalent circuit. Thevenin's equivalent circuit, which consists of Thevenin's voltage and Thevenin's resistance. This Thevenin's resistance is also called as source resistance or internal resistance of the circuit. Now the complete network is connected with one resistor. That resistor is load resistor, variable resistor value. This RL value is changing now. So now the complete linear network is replaces with the Thevenin's equivalent circuit and load resistor is connected as it is. Then I want to find out the power of the load resistor. To find the power, here I am finding initially first I. Current through the load resistor I. So current through the load resistor RL I is voltage, total voltage by total resistance. So total voltage is V Thevenin's and total resistance is R Thevenin's plus RL. These two are connected in series combination. Total resistance I wrote here. I is equal to V Thevenin's by R Thevenin's plus RL. And according to the theorem here we have to find out power. So first write the power equation. Power is equal to, total power is equal to, general formula is I square into RL. Here I want to find out power dissipation of the load resistor RL. So that power is equal to I square into RL. Current through the circuit is I and RL resistor is there, I square into RL. I equation I wrote there, substitute in this. If we substitute the equation here, V Thevenin's by R Thevenin's plus RL whole square into RL it gives here. V Thevenin's by R Thevenin's plus RL whole square into RL. This gives the power equation. Then what we required from the theorem analysis, we required maximum power. So one equation is given here. To find the maximum condition of this equation, immediately we have to apply one mathematical operation. That mathematical operation is differentiate the complete equation and apply equal to 0. To find the maximum, of any one equation, there we have to perform differentiation operation. Differentiate the complete equation and apply equal to 0. So now I am differentiating this power because I want here maximum power condition. So to find that purpose, differentiate this power with respect to load resistance RL and apply equal to 0. This complete equation is we have to apply differentiation operation with respect to RL. So with respect to RL operation, so apply here U by V representation, differentiation of U by V, then apply equal to 0, then it gives the one condition, that condition is directly which gives the R Thevenin's is equal to RL. R Thevenin's is equal to RL. So if you differentiate this complete equation with respect to load resistor RL and apply equal to 0, then it gives you one condition R Thevenin's is equal to RL. That means if the load resistance is equal to the Thevenin's resistance, that means source resistance, internal resistance of the complete circuit, if these two are equal, then the power consumption of the load resistor is maximum. The power consumption of the load resistor is maximum. That maximum power now I am writing here. That maximum power P max is equal to power formula is this equation. In this equation, I am substituting here R Thevenin's is equal to RL. Substitute here R Thevenin's is equal to RL. So now it gives the RL plus RL whole square into RL. If you simplify this, directly it gives the V Thevenin square by 4 RL. So from this theorem now, from this analysis here, we can write one simple point here. The point is the power dissipation of the variable load resistor RL is maximum. The power dissipation of the variable load resistor RL is maximum if the load resistance is equal to Thevenin's resistance. Load resistance equal to Thevenin's resistance, both are equal, then the power dissipation of the load resistor RL is maximum. And the maximum power is V Thevenin square by 4 RL. The maximum power is V Thevenin square by 4 RL. This is maximum power equation, and condition for maximum power is R Thevenin is equal to RL for DC circuits. If the circuit is DC circuit, the power consumed by the load resistor RL, the power consumed by the load resistor RL is maximum if RL is equal to R Thevenin's, and that maximum power is equal to V Thevenin square by 4 RL. So now this complete analysis, now I am drawing with one graphical representation here. The graphical representation I am taking here, one resistor is load resistor. Load resistance is variable resistor because I wrote here one arrow mark representation. This load resistor value is changing from 0 to infinity, and one more axis I am writing now, power of the load resistor. So Thevenin's resistance is some fixed value is there. I am assuming the Thevenin's resistance is here. Exactly, it gives the Thevenin's resistance is here. Now from this equation here, from the maximum power equation, I am writing here efficiency. Efficiency in terms of percentage. Efficiency general formula is output power by input power. Here output power is the power of load resistor by input power means the total power. Total power is here Thevenin's resistance power plus load resistance power. Power by load resistor power, output power by this output power by input power. Input power is nothing but power of the R Thevenin's resistance plus power of the load resistance RL. Then I am writing equation here, I square into RL. I square into RL into percentage is there into 100 we have to write here. So I square into RL. Power of R Thevenin square is I square into R Thevenin's plus I square into RL. So I am taking I square is common, then it becomes R Thevenin's plus RL. R Thevenin's plus RL. Then finally the equation is load resistance by Thevenin's resistance plus RL into 100. So load resistance by Thevenin's resistance plus RL into 100. This is a standard equation of efficiency here. So here I am discussing your efficiency because here the complete analysis is explained with power. So wherever power is used, means power analysis is used, immediately we have to find out efficiency, because efficiency explains the power consumption of the circuit. So input power is connected to the circuit, what is the output power of the circuit? And output power and input power both are equal, then the power dissipation of the circuit is 0. So the complete circuit analysis explains the power dissipation of the circuit. That purpose always you have to take efficiency operation. So efficiency of the given circuit is RL by R Thevenin's plus RL into 100. R Thevenin's value is your constant value, that value is fixed value. Here I am assuming this is R Thevenin's here. This is R Thevenin's. And this side, this RLE value is varying here. This axis is RL axis. R Thevenin's value is here, some value is there. So from here to here, this condition explains the load resistor value is less than the R Thevenin's. Load resistor value is here 0 to increasing like this. So load resistance value is less than the R Thevenin's here. And this side explains the load resistor value is greater than the R Thevenin's. Load resistor value is greater than the R Thevenin's. Suppose this R Thevenin's is 10 ohms. R Thevenin's is 10 ohms. Initially RL is 0, less, 1, less, 2, less, 3, 4, 5, 6, 7, 8, 9, 10. Exactly at 10, RL is equal to R Thevenin's, this condition. And later RL value is increases and R Thevenin's value is 10 here, and 11, 12, 13, 14. So those values are greater than the R Thevenin. So the complete axis is divided into 3 parts. One part is RL is less than the R Thevenin's, and another part is RL is equal to R Thevenin's, and one more is RL is greater than the R Thevenin's. So initially I am finding here first power and power equation. Power equation is there here, and in this I want to find out power, and similarly I want to find out efficiency also. So first initially I am taking RL is less than the RThevenins. This condition explains the maximum power occurs at RL is equal to RThevenins. So exactly at this point it gives the maximum power. This gives the maximum power. Other than this condition, power is less. So the power is increases like this. The load resistance and power relation it gives it like this. Let us assume RL value is 0. RL value is 0. Substitute here 0 here. RL is 0. If RL is 0, the total power is 0. So power is 0. And power is maximum with RL is equal to RThevenin. So at RL is equal to RThevenin, power is maximum. Then it gives the maximum power. And load resistance is very high value. Very high value means just I am assuming infinity. Substitute RL is equal to infinity here. Something by infinity becomes 0. So if the load resistance is very high, then the power of the load resistance is 0 watts. The power of the load resistor is maximum at one condition, only one condition. The condition is RL is equal to RThevenin. Exactly at this point it gives the maximum power. Now I want to write efficiency of this analysis. Efficiency is less than the 50%, greater than the 50%. All these points I want to write here. So to write the purpose, initially I am taking RL is less than the RThevenins. Otherwise first take this condition. RL is equal to RThevenins. Both are equal. RL is equal to RThevenins, then substitute in this RL is equal to RThevenins. Both are equal. 2 into RL. RL cancel. 1 by 2 into 100, that gives the 50%. So exactly efficiency is 50% at RL is equal to RThevenins. RL is equal to RThevenins, efficiency is 50%. This point is important. If any circuit satisfies the maximum power transfer theorem in DC circuits, any circuit satisfies the maximum power transfer theorem, then the efficiency of the circuit is 50%. Exactly at this condition it gives the 50%. This is finished. Now I am taking this condition. RL is less than the RThevenins. This value is less now. This value is less. For easy understanding purpose, just I am taking few values. RThevenins is 10. RThevenins is 10. RL is 1. So 1 by 10 plus 1, 11. 1 by 11 value is 0.1 something here. So 0.1 into 100 gives it 10%. 10% is nothing but efficiency is less than the 50%. Efficiency is less than the 50%. If the load resistor value is less than the Thevenin's resistance, then the efficiency is less than the 50%. This point is important. This point is important. Similarly, we have to write this side also. Now RL value is very high. So here I assumed RThevenin is 10 for easy understanding purpose. Now I am taking RL is also 100 value. 100. So then it gives the 100 by 10 plus 100. 10 plus 100 becomes here 110. So 100 by 110 is approximately it gives the 90%. 100 by 110 is approximately it gives the 90%. So this side it gives the efficiency is greater than the 50%. See, the efficiency of the circuit is changes with respect to the load resistor RL. If the load resistor RL value is less than the RThevenins, load resistor RL value is less than the RThevenins, efficiency is less than the 50%. If the load resistance is exactly equal to the RThevenins, then the efficiency is 50%. If the load resistance is greater than the RThevenins, then the efficiency is greater than the 50%. So these points also important. So now just note on all this. Later I will explain the important points from the maximum power transfer theorem and the statement of the maximum power transfer theorem.
Thank you very much guys for watching all the videos. So far what we have completed, let's discuss about it now. Over the screen you can watch SAIMEDHA.in app. If you open the app guys, you are going to see there. Let's talk about the store now. In some other branch, let's open a EEE branch guys. In the EEE branch you can see the content. In the content engineering, in the engineering we have electrical circuit, 75 videos there. In that mesh and nodal analysis, if you open, you can see there we are having around 11 lectures guys that we have completed. Then practice set 1, practice set 2 with solutions, questions with solutions, practice set 3, questions with solution, previous ecet questions with solutions, and at last we have what mesh and nodal analysis practice sets. So what we have covered guys, we have completed all the basic to advanced level video lectures. Then we have completed the practice set 1, set 2, 2, set 3. Each set is going to have around 20 to 100 questions there guys, based upon the topic marks. It is going to be there in the not only in ecet but also in the government jobs and PSUs. And at last you have there an online test examination also, in order to check the time management what you need to utilize in the competitive examinations. So this is so far we have completed guys. Now you can watch over the videos. It can be utilized for, it is useful for not only the ecet examination but also for DRDO, sub engineer, assistant engineer, Telangana State Public Service Commission, Andhra Pradesh Public Service Commission, BHEL, NTPC, IOCL, Staff Selection Commission, JEE. I remind guys, for ECEEE and civil, this SSC JEE will be there every year twice. So make sure you utilize all the video lectures to prepare for this examination also. And everyone knows about the Railway Recruitment Board Junior Engineer and as well as ISRO guys. If you people are interested to watch all the full length videos in the SAIMEDHA.in app, make sure you save this number. This is in charge sir Shashikant Valmiki sir number guys, 98486925998. Give him a missed call, give him a call guys for any details, for any updates. Every single day we are updating the videos, material, and as well as what a competitive level examination practice set papers also. Thank you very much guys. I wish that you have watched all the videos. If you haven't watched so far, go and refer all the videos guys. Thank you very much. This is Mohammad Inzamam signing off.